Hello, I'm Lindsay Fiorelli, and today I'll be presenting my summer research project on acoustic levitation and the acoustic radiation force. This study explores how the variation of an acoustic pressure field may be used to control the movement of levitated water droplets. An object immersed in an acoustic field experiences a force exerted by the acoustic wave, called the acoustic radiation force. When the sound intensity and therefore the momentum of the propagating sound wave is sufficiently high, an object such as a drop of water can be levitated against gravity. Levitation occurs when the acoustic radiation force is strong enough to counteract the force of gravity. The pressure exerted on the surface of a particle, or water droplet in our case, is called the acoustic radiation pressure and is caused by the acoustic radiation force. The force on the particle is a result of the particle's finite size, such that the gradients in the pressure field will result in greater force being exerted on one side of the particle than the other. As seen in the figure, the acoustic radiation pressure is not homogeneously distributed on the surface, being positive at the upper and bottom surfaces and negative at the equator area. Though there are several types of acoustic levitation, this project will specifically be focusing on standing wave levitation. In a standing wave levitator, particles are trapped at the nodes of an acoustic standing wave formed by a source and a reflector. The source vibrates to generate the acoustic wave, and the reflector reflects the wave to cause standing wave interference. Here you can see a Schlieren air density photograph of a standing wave produced by our ultrasonic transducer at 100 watts of output power. The half barbell horn, which you can see at the top, is attached to the transducer and separated by a distance of 38.6 millimeters from a metal reflecting plate at the bottom. In a barotropic fluid, like air, variations of pressure are proportional to the variations in density, so we are able to observe the standing pressure wave pattern through the banding pattern. Acoustic levitation provides a means of avoiding contact with a solid surface. This is important for systems that must be free of surface interactions. A wide variety of materials can be acoustically levitated, whereas other forms of levitation, such as electrostatic or magnetic, require special material properties. This advantage makes acoustic levitation a versatile tool for studying physical, chemical, or biochemical characteristics of liquid samples in containerless conditions, without interactions between samples and the container walls. Recently, I had the opportunity to attend a webinar by Professor Monica Rich-Marte from the Medical University of Innsbruck, where she discussed the need in biomedical investigations to move, stretch, or mechanically probe a biomedical sample in a non-contact way. Acoustic trapping is being looked into as a means of exerting controlled forces on small objects. The images show the acoustic trapping of one such sample, a large, actively moving, live tardigrade. The long-term goal of this project is to send light through a system of levitated particles to better understand the interaction of light with the water droplets in a maritime environment. Studying these interactions is of interest for environmental sciences as well as commercial and military sectors. Again, the acoustic levitator is made of two key parts: the transducer, which is connected to the horn you see at the top of the video, and the reflector, which is at the bottom. The reflector is placed opposite of the transducer at a distance corresponding to an integer multiple of half the wavelength of the sound wave. This space is called the acoustic chamber and is where levitation will occur. The transducer vibrates with a frequency of 20 kHz, emitting acoustic waves that travel inside the acoustic chamber until they are reflected back by the reflector. The interactions between the emitted and the reflected acoustic waves create an acoustic pressure distribution inside the chamber with areas of high and low pressure. The points of levitation, called the trapping zones, are found at the nodes of the standing wave, where the pressure is at a minimum. In the video, I am introducing the water droplets by misting the system with a syringe. The mist converges at the nodes while avoiding and falling off of the antinodes. The trapping force that suspends the drop against gravity is significantly stronger than the trapping force which holds the water drops horizontally at the center. To record the dynamics of the water droplets in the trapping zone, an Edgertronic high-speed camera is placed perpendicular to the levitator. The quality is obviously much better than this video taken on my phone and allows for close-up investigation of a single trapping zone. The trapping zone is illuminated for the videos with a high brightness blue LED source to ensure high quality imaging. Here is an example of a slow motion video taken by the high-speed camera. This shows a droplet with a radius of 0.5 millimeters oscillating at trapping zone B. Each video has an approximate frame rate of 490 frames per second, so 1 second in real time is represented by about 15 seconds in the video. As you can see, the droplet is experiencing oscillations in both the horizontal and vertical direction. The maximum displacement of the droplet during these oscillations varies across the videos. The relationship between the mass of the droplet and the amplitude of the oscillation was examined, but after further investigation, it appears that these two effects are independent of one another. Instead, the variation appears to be caused by collision factors during the formation of the droplet, which we will see more of next slide. By using the period of these oscillations as well as the mass of the droplet, an estimate of the effective trap stiffness can be calculated. The horizontal trapping range is significantly smaller than the 45 millimeter horn diameter, and the vertical trapping range is nearly equal to the maximum stable trapping range. The horizontal and vertical periods of oscillation are measured to be 0.3 seconds and 0.05 seconds respectively. The effective trapping stiffness values are determined from the expression, where K is equal to the mass times 2 pi over the period squared. We find that in the horizontal direction, the trapping stiffness is approximately 0.23 times 10 to the negative 3 newtons per meter, while the trapping stiffness in the vertical direction is 8.2 times 10 to the negative 3 newtons per meter. An effective value is used because the droplet is driven in the acoustic field, driven by the acoustic field into a sustained oscillation and is not freely oscillating. As expected, the acoustic trap is much stiffer in the vertical direction than the horizontal direction. This approach is again used to find the values of the average effective trapping stiffness at 3 different nodes. A separation distance of 2 times the wavelength is used, which allows for 4 planes of levitation to be visible. The average effective trapping stiffness is determined for the trapping zones A, B, and D, with zone A being the bottom node closest to the reflector and zone D being the top node closest to the transducer. As of now, we do not have a trapping stiffness value for trapping zone C, which exhibits dynamics differing from those of the other 3 nodes. Instead of having a stable central point for trapping to occur, levitation plane C seems to have a circle of trapping points, where the droplet can freely move along the circumference. We plan to further investigate levitation plane C moving forward. In order to determine the mass, the shape of the droplet is approximated as an oblate ellipsoid. The horizontal periods of oscillation are measured to be 0.2 seconds at A, 0.3 seconds at B, and 0.5 seconds at D. The average effective trapping stiffness values determined from the same K expression as before is 2.76 times 10 to the negative 4th newtons per meter for A, 1.29 times 10 to the negative 4th newtons per meter for B, and 8.27 times 10 to the negative 5th newtons per meter for D. These results indicate that the acoustic trap may provide a means of studying laser-driven optomechanical droplet dynamics. An equivalent radiation force, from a laser focused on the droplet, 2 times the power over the speed of light, would require a laser power on the order of 100 watts. A more modest power of 10 watts would produce measurable results, affecting the oscillation amplitude and period. Since trapping zone D has the weakest average effective trapping stiffness, laser beam experimentation will primarily be focused there. However, we plan to fully explore the odd dynamics of trapping zone C as well. Its circular trajectory may provide the weak horizontal trapping stiffness needed for laser beam interactions. All right, I would like to thank my advisor, Professor Grover Schwartzlander, as well as the School of Physics and Astronomy and the School of Imaging Science at RIT, and all the members of the Organizing and Planning Committee for this year's Undergraduate Research Symposium. And finally, to all those who took the time to see my presentation, thank you and have a great rest of your day. If you have any questions, please leave a comment below and I will try to get back to you. Thank you.